Assalamualaikum and good day. Today we continue a little bit on controller tuning relation. So previously we have learned on IMC tuning relation. So beside IMC, we have another tuning relation based on integral error criteria. So three popular integral error criteria are integral of absolute value of error IAE, integral of squared error ISE, and integral of time weight absolute error ITAE. So this is the graphical interpretation of IAE, integral absolute error. So if you can see that it is the value under the graph, right? So this is the graphical interpretation of IAE. Okay, so basically you can refer to this table, table 12.3, in order to calculate the controller setting using ITAE relation, tuning relation. So you have both for disturbance and set point change. Okay, if you look here, you have P, I, and D. So what's the meaning of P, I, and D? So if you want to calculate for proportional parameter, you refer to P rows. If you want to calculate the tau I, you refer to the I rows. And if you want to calculate the value of tau D, you refer to the D rows. But you need to use the design relation as given here, where y equal to k times kc for proportional, y equal to tau over tau I for integral, and y equal to tau d over tau for derivative mode. But for set point change, the design relation for integral mode is given here. Okay, so later we'll look at the example on how to use this table. You can also find other tuning relation given by Heckman and Estrom, as well as a co-gifted tuning relation, but this will not be tested in your exam. Okay. Now let's take a look at example 12.5. A blending system with a measurement time delay can be modeled as this. So you know that this is your time delay. Time delay equal to 1.07. And this is your tau. And this is your k. So k equal 1.45. Tau equal to 5.93. Now calculate PI control setting using the following tuning relation. IMC with tau c equal to tau over 3. So tau over 3 is 5.93 divided by 3. And using IMC with tau c equal to time delay. So time delay is tau c equal to time delay. Time delay is 1.07. And using ITAE for disturbance change and ITAE using set point change. Okay, now for part A and part B, because you want to calculate PI setting using IMC tuning relation, so you need to refer to table 12.1. So this is table 12.1. So according to the model, this is first order plus time delay model. So which case do you need to refer here? Of course, case G, because this is for first order plus time delay model. Okay, the question is why we don't use case H here? Because you want to calculate PI controller. If you want to calculate for PID, so you use case H, because you have all the parameter, all the PID parameter here, Kc, tau I, and tau D. For this one, This is for PI controller setting. Okay, so according to this table, okay, your KC, K based on case G will be equal to tau over tau C plus time delay. And tau I equal to tau. So now let's substitute the numerical value. So this one, K you bring to this side. So 1 over K times tau C plus time delay. So now your tau C is what? Tau C just now equal to tau over 3, which is equal to 5.93 divided by 3, which is also equal to 1.97. So now substituting the numerical value, 1 over K, your K is 1.54, tau is 5.93 divided by tau C is 1.97 plus time delay is 1.07, which gives you the value of K equal to the value of KC equal to 1.27, and your tau I equal to tau, so your tau value is 5.93. So you get your PI control setting using IMC with tau C equal to tau over 3. So you have your the value for KC and tau I. Okay, next, using the same method IMC, but with tau C equal to time delay, so your tau C equal to 1.07. Okay, similarly, you're still using case G, so your KC is equal to 1 over K, KC equal to 1 over K times tau over tau C plus time delay, which is equal to 1.54 times tau 5.93 over tau C equal to time delay, which is equal to 1.07 plus time delay 1.07, which gives you the value of 1.8 or 1.79, and tau I is equal to tau, which is equal to 5.93. So you have your PI controller setting of KC and tau I value of 1.8 and 5.93 respectively. Next, for part C and D, you need to calculate the PI's controller setting using integral of time weight absolute error ITAE. So you need to refer to table 12.3. Okay, for part C, you need to calculate for disturbance change. So we refer to the first row for disturbance change for PI controller. So the first row here, P here is to calculate the value of a proportional parameter, which is KC, and I here to calculate the parameter for integral controller, so which means to calculate the value of tau I. So now, according to the table, so you are given with this expression. So first to calculate the KC value, so K times KC equal to A times time delay divided by tau to the power of beta. So substituting the numerical value, we know that A equal to 0.859 times time delay 1.07 divided by tau is 5.93 to the power of B, which is negative 0.977. And to calculate Kc, we bring K over here, so multiply by 1 over K. Your K equal to 1.54, which give you the value of Kc, which is equal to 2.97. And then for integral parameter, so we want to calculate tau I value. So based on the relation given here, so tau over tau I equal also this relation but with different value of A and B. So now A is for tau I, A is 0.674 times time delay over 5 point over tau to the power of beta, which is to the power of B, which is equal to negative 0.680. And bringing that, because we want to calculate tau I, so you bring this to this side, so tau I equal to tau over this value, which is equal to 2.16, and your tau equal to 5.93 over 2.16, which will give you the value of tau I of 2.75. So you get the value of Kc and tau I. Last but not least, for set point change, you need to refer to this row. So the value of K times Kc will be equal to, using the same relation as in part C, but different value of A and B. So now your A is equal to 0.586 times 1.07 over 5.93. The power of B, your B now is negative 0.916. So to get Kc value, you bring the K over here to the right side. So your Kc now equal to 1.83. Okay, done with Kc value. Now for tau I, you need to use this relation. So tau over tau I equal A plus B time delay over tau. Now your A is 1.03 plus minus 0.165, which is the value of your B. Okay, times the time delay over tau, which is equal to 1. So now to get the value of tau I, we divide tau with 1. So your tau is 5.93 divided by 1, which gives you 5.93 for tau I. So you get value of Kc and tau I. So what can you conclude from the findings? It is found that the ITAE disturbance setting are the most aggressive, while the IMC setting with tau c equal to tau over 3 is the less aggressive. Okay, this is due to the highest value of Kc and the lowest value of tau I for this setting that make it become the most aggressive, while for this setting it has the lowest Kc values and tau I and highest tau I values. So if you can recall from chapter 8, increasing the value of Kc will make the process become faster or more aggressive, while increasing the value of tau I will make the process more sluggish or less aggressive. So if you check using Simulink, you can see the difference. So you can see that this setting, okay, support the theory in chapter 8. Okay, and beside that, if you look at these two settings, you can see that they have almost identical values of Kc and tau I for this example only. But this is not true in general. Okay, that's all. Don't forget to fill in the attendance form. Thank you.